So these are notes on the movement of plates and plate boundaries. These plate boundary notes start about halfway down the page, and we'll do the rest of those notes at some point. But I wanted to talk about how the plates actually move. The plates move because of convection currents within the asthenosphere, and we talked about that asthenosphere, this layer in the earth, the upper part of the mantle, that is this part right here that is plasticky. It's like that silly putty that we talked about, or that I showed you. And the plates themselves, the upper part of the mantle and the crust, ride on top of that asthenosphere. And the currents within that cause the plates to move. And we'll see that with the lava lamp when I show you that example, where you have warm, less humid, warm, less dense material rising to the surface, and then it cools off, and then it sinks back down. And that movement is actually what's causing these plates to move. If we look at what a convection current is, convection currents are caused by differences in density. And we saw this in 8th grade. You saw this in 8th grade with weather. And the reason why weather happens and wind happens is because the Earth's air heats, the atmosphere heats, and it causes differences in density. Rising currents cause the plates to move apart. They're called divergent boundaries. Places where the are moving together or convergent boundaries is caused by these currents that are falling. And if you look here, this right here is a divergent boundary. One plate's going to the right and one plate's going to the left, and it's because this is rising and separating here, and as this moves and separates, it causes these plates ride along like a conveyor belt, and they move along and then come back down. And this is a convection cell. This little loop of arrows is called a convection cell. And so these rising and falling currents cause the plates to actually move, and the plates just sort of are along for the ride. And it all, again, has to do with density. The continental crust is made out of granite, which is a density of about 2.7 grams per centimeter cubed. It's generally thicker than the ocean. The oceans are generally thinner. They're made out of basalt. They have a density of 3.0. So if you have an ocean and a continent come together, if they collide, which one is going to stay above the other? Well, the one that is less dense rises over top of the one that's more dense. So the ocean is going to go down underneath the continent, and we'll see that happening when the plates collide. And we'll talk more about that with the collision boundaries. Divergent boundaries are where two plates are moving away from one another. And you can see in this diagram down here that heat is rising, it separates at the surface when the heat rises and gets to the top of the asthenosphere, and it starts to spread out. When it does that, one plate goes one way, you can see here, and the other plate goes the other way. And what you get when two plates separate is you get a ridge, what's called a mid-ocean ridge, forms here. And if this happens in a continent, if a continent starts to split apart, that lower area will begin to fill with water, and you'll get a new ocean forming there. The youngest rock is going to be located near the center where this starts. So new rock is bubbling up here, and the lava is hardening and causing new rock to be formed. And as you move further away, these rocks used to be at this mid-ocean ridge. They've been pushed away as these convection currents cause these two plates to move. It causes those plates to move apart from one another, and the rock gets older as you go further away. The center is where the newest rocks are forming. You will see this in the activity on Friday, and this has to do with the age of the bedrock. This age of bedrock, you can see the youngest rock is here at the 0, the oldest rock's up here. And if you had to make a guess as to which areas there are going to be divergent boundaries, well, the divergent boundaries should be where the youngest rock is. youngest rocks forming at those divergent boundaries. So if you look here, the youngest rock is this red, and you can see on either side of this boundary there's the divergent boundary. As you go away from that center point, the rocks get older as you get further away on both sides, and they match both on both sides. That's one of the pieces of evidence that we have for these divergent boundaries, is that these rocks get older as you get further away. Another piece of evidence that sort of shows us that these rocks are being created here is that some igneous rocks or some volcanic rocks contain minerals that are magnetic. And if you get very, very sensitive instruments that measure small changes in magnetism, we can see at the middle of the ridge, as you go on either side of the ridge, there's what's called a magnetic reversals. And in the Earth's history, there were times when the Earth's magnetic field changed polarity, where the North Pole wasn't the North Pole. The North and South poles switched. So if you go outside with a compass, what would normally be pointing north is now pointing south. And what ends up happening is, as these rocks solidify, the magnetic orientation gets solidified in the rock itself. And if we have normal polarity being these rocks, if these striped rocks here are reverse polarity, where the North Pole is not the North Pole, but it switches and becomes the South Pole, this matches on each side of this mid-ocean ridge, which means that these two striped rocks were formed at the same time, and then they get pushed out from that center point. So the crust shifts, and this magnetic reversal, these bands of magnetic polarity where you have positive, normal, and reverse polarity, they match in bands going out from that center point. And it actually kind of looks just like this. If this is age, this could be, if it wasn't age, it could be magnetic polarity, where this is reversed. The green is reversed, and the yellow is normal, and this orange is reversed, and the red is normal. So you get these bands of normal, reversed, normal, reversed, normal, reversed on both sides that match up. And the only way that we've been able to make sense of that is that because these rocks are moving from that center point, it gives us those bands of rocks. The evidence that the Earth's moving apart at these divergent boundaries: the ocean floor is younger than the continents. Continental rocks continually form at the mid-ocean ridges. Heat flows highest at that center. Lava's leaking out. It's very hot there. You get these underwater volcanoes, and you get these magnetic reversals. All of these things tell us that the plates are moving apart at those divergent boundaries in the center of the ocean. And most of these divergent boundaries are in the center of the ocean, because that's what's the type of rock that's forming is oceanic crust. That's all for now.